All right, welcome to this next video for Chem 161, touching on some Chapter 6 materials, specifically relating to solubility. And so we'll first just comment on some general terminology and definitions here to help us. So what we have in trying to negotiate properties like solubility, does material dissolve, is the idea of whether or not the solubility of the solute will be compatible with the host solvent. Okay, so the solubility of solutes with both polar and nonpolar groups in a polar solvent will decrease as the nonpolar groups increase. Okay, so we'll see here that, a solute, something trying to dissolve, will try to find an alike part of a molecule to favor compatibility and ultimately see if it can dissolve. So polar will seek out polar parts of a molecule, and nonpolar solutes will try to seek out nonpolar parts of a molecule if that's possible. Okay. So to help us with this idea, we have some additional terminology here. We have the term hydrophobic. So phobic means fearing, like arachnophobe, you're afraid of spiders. Hydro, of course, means water, so we have water fearing as a term there. And so this is a good term to use when describing nonpolar components of a molecule, for example. Okay, so things like our very nonpolar CH bonds program for a lot of nonpolar areas in molecules. Okay, so hydrocarbons are very non-polar. And a hydrocarbon is, of course, made up of things that are built on carbon chains with hydrogens all the way around, so thus the term hydrocarbon. Okay, so note there that hydro here this time refers to the hydrogen atoms, a little different than the word hydro or the prefix hydro and hydrophobic. Hydrophilic. Okay, philic means liking or loving. So here, hydrophilic would indicate water loving. And so this would be used to describe polar solutes or species that we're considering dissolving, or polar groups on molecules to help us there. So we've previously seen the alcohol group, which was the OH feature that could be installed on certain molecules. And we know that this is both polar and capable of hydrogen bonding. And this would therefore lead to compatibility with other species like that. So water would be compatible with the alcohol functional group of many molecules, should they be there. Okay. And so to guide us through all that, we have the idea of kind of matching polarity or matching these hydrophobic and hydrophilic parts of molecules. And a way to help us with that, we have the sort of saying like dissolves like. So polar dissolves polar, nonpolar dissolves nonpolar. Okay. So here's a data set that we can look at that touches on solubility. Okay, so let's clean this up so we can inspect this. And if we look down the chart, we have an alcohol series. We've seen this before in a previous video, so if you're unfamiliar there, please check that video. But essentially, we have the alcohol functional group OH installed on every molecule. It's at the end of the chain of these alkanes, and because that OH is installed on the alkane, we'll call it an alcohol. And we see that we start with the shortest carbon version of that, methanol at the top. Ethanol has 2 carbons in the chain. Propanol has 3 carbons in the chain. Butanol 4, etc. Okay, so you see we walk all the way down to a C7 chain for heptanol. And we've got 2 data tables. We've got the solubility in water, and we've got the solubility in hexane. So hexane is a hydrocarbon that is CH3, CH2, 4 times, and then a final terminus of CH3. So it's very similar to the hexanol, except that the terminus is not OH, it is CH3. Okay. So we can see here that for short carbon chain alcohols, like the top 3, that the alcohol functional group is pretty dominant in the molecule. It's making up a significant proportion of the molecule. So the polar alcohol group is strong enough in content that it is programming for good compatibility with polar water. So we have solubility that is infinite. That is to say, we can mix anywhere from 1% methanol in makeup water, or we can be 99% methanol in makeup water, and vice versa for ethanol and propanol. And of course, to even more extreme than simply 1 in 99 cases, to very minor amounts as well. Once we start extending that carbon chain too far, so we go to butanol now where we have 4 carbon chains, you can see here that we have a solubility limit. So that is to say that only a certain moles, a certain number of molecules of that alcohol will dissolve in 100 grams of solvent at room temperature. So butanol, 0.11 moles of that alcohol are capable of fully dissolving in 100 grams of solvent. As you extend the chain even further, C5, C6, C7, you can see here that the solubility limit drops dramatically. So we get to very small molar quantities of that alcohol being compatible with 100 grams of solvent. Okay. Exceeding these proportions, if you want, of the moles of alcohol and solvent, you would be in a situation where there's insolubility. Okay, so an insolubility would result where you would have a 2-layer system, where you would have an oil type phase resting on top of a water type phase, like you may have seen in your vinaigrette salad dressing, or that you're familiar with oil spills on the ocean. Oil is lower in density and tends to float on water. And so we would expect that past the solubility limits here, that we might see some of these alcohol liquids floating on water, and only the water down here would have a little bit of the alcohol dissolved, reflected in the values that we see in the table here. Okay. Now, we might expect the opposite trend to result if we're working with an opposite solvent. So here, working with a very nonpolar hexane solvent, we get infinite solubility in the hydrocarbon rich, the very long carbon chain rich molecules, where the alcohol group is non-dominant, kind of diluted for the number of CH2s and CH3 in the rest of the molecule. And it's not until we get to a very low kind of carbon chain content that we see a limit for how much of methanol that is compatible with hexane. So methanol would also kind of phase separate from hexane if we exceeded a target value of 0.12 moles per grams of the solvent that is hexane this time. All right, so this like dissolves like can help us rationalize solubility trends for molecules that have both polar groups and nonpolar chains or groups, and help us rationalize solubility properties. Okay, so here this is not only interesting just for things like oil spills on the ocean, but it's actually very vital to how life works. And so here's vitamin A and vitamin C. And you can see here that one is very CH rich, a lot of CH3, CH2, CH bonds. a lot of non-polar content in vitamin A, with one small polar alcohol group at the end. And the other, vitamin C, is very alcohol group rich and more muted in the CH content. So we might expect that vitamin A is going to be very soluble in non-polar compounds like fats. So we say that vitamin A is fat soluble, perhaps something you've heard from other nutrition type courses or experiences. And vitamin C, with its rich content of alcohol groups, is more water soluble. So we say vitamin C is very water soluble as a consequence. Okay. So you should be able to answer questions like this now. Like dissolves like is the theme here. So why might ethanol dissolve in water, but why doesn't hexane dissolve in water? Here's the observation. You might be familiar with your parents' alcohol drinks. And so we know that there's a certain ethanol content in this spirit drink here that is a martini. So there's ethanol and water, very compatible and dissolved, no phase separation. However, you install hexanes, which is that CH3, CH2, 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 CH3 molecule that completely avoids water, does not disperse, it phase separates, and we have essentially pure water down below. And there's immiscibility, does not dissolve. So hopefully you're pointing to reasoning here that is aligned with some of these options here. So maybe you pause the video a moment here and answer the question, and resume once you have your answer. Good. So hopefully you rationalize that the first three answers are wrong and the last three is correct, and that the hexane has very poor intermolecular attraction to the water, given the polarity of the water molecule. And this weak intermolecular attraction to water does not allow solubility, but the ethanol has compatibility with the water. Here's the ethanol molecule, and so we would expect the delta plus and the delta minus on opposite ends of these to interact with one another and therefore favor ethanol compatibility with water. So this is why ethanol dissolves in water. Answer D. Okay, and last, you should be able to handle questions like this. So here's some to practice your concepts. So you could compare dimethyl ether, formula shown below, to ethanol, formula shown below, and answer questions like this. Which would have the strongest intermolecular forces? Which would have the lowest boiling point? Which one would have the higher vapor pressure? And which one is more soluble in water? So if you haven't had a chance to see what vapor pressure is the pressure due to molecules in the headspace above liquid in a closed container. Okay, so we can kind of draw a closed container, put some liquid in it. Molecules from this liquid will leave that liquid and establish the vapor in the headspace above that. And the vapor pressure is the pressure due to the presence of those molecules in that headspace. Okay, so clearly a requirement to get a lot of vapor pressure would be allowing molecules to break away from the bulk liquid and install themselves in the headspace above. Vinegar has a very high vapor pressure because it quickly establishes the smell of acetic acid vinegar above the headspace of liquid vinegar solution anyway. Okay, so see if you can pause the video and address these questions and check your work when you're ready. Okay, so hopefully you started by drawing the molecular geometry to help you predict polarity and ultimately think about intermolecular forces, that is, forces between twins of these molecules. And so the strongest intermolecular force would be for the molecule here, where we have not only do we have London dispersion forces, every molecule and atom has that, but we should also have dipole interactions because of the polarity installed by the oxygen group. And of course we have FON, we have the requirements satisfied for hydrogen bonding as well. 3 forces at play there. Whereas over at left we'll only have dipole and London dispersion forces. Okay. In B, which would have the lowest boiling point, so as a consequence of answering A, you should be able to predict that the lower boiling point is going to be the one with the weaker intermolecular forces, and so that is going to be the dimethyl ether, the green compound, lower boiling point than that of the ethanol, here found at 78 degrees C. Higher vapor pressure, so which one is going to put more molecules in the headspace above a puddle of itself? So we want to have the compound that can allow for molecules to break away from the liquid more successfully. So this means breaking intermolecular forces to release those molecules into the headspace. So this one is going to be the dimethyl ether is the answer there. And which one would be more soluble in water? So we're looking for like dissolves like to try to get as many of the intermolecular forces compatible with that of the water. Water has a hydrogen bond. Water has dipole, and water has London dispersion forces. So we're going to have a lot of compatibility there, and only a couple of those boxes are checked for the dimethyl ether. So it is the ethanol that's infinitely soluble across all proportions, which is differing than the dimethyl ether that has a solubility limit of only being able to dissolve 33 grams of that green compound in 100 grams of water. Okay, so this is how you work with these properties to predict things like whether or not compounds can dissolve and ultimately trends in those limits of solubility.